This is a detailed walkthrough of how to use and fine-tune multimodal audio plus text models. The specific model we'll focus on is Qwen 2 Audio, which allows for text and/or audio input and provides text output. This is interesting for a few reasons. You can build a voice assistant that responds with text, transcribe text in a way that also includes information on emotions, do zero-shot transcription of new or unfamiliar words, or do acoustic analysis, say of machines or perhaps wildlife. I'll cover all the way from the basics of how these models work, how you can customize them for your specific application, and then deploy them at commercial scale using VLLM for inference. I'll start by going through details of the Qwen 2 audio and text model. Then I'll describe the benefits of using this integrated multimodal model, say versus cobbling together Whisper and then a language model afterwards. I'll talk about the applications where this combined text and audio is particularly useful. And then I'll go through Colab Inference. So that's quickly running the model and testing it out in different ways with a free Colab notebook, followed by fine-tuning. So I'll show you how to generate a data set that you can use to then fine-tune the model for your application. And lastly, I'll cover how you can deploy this for production-grade inference using VLLM. So let's take a look at the paper. There is a fairly brief technical paper available on the Qwen 2 audio model, and it shows this diagram here of how the model works. It takes in both text and audio. It puts the audio through an encoder, which is actually a Whisper large model, and that converts it into vectors that are then adapted through a linear layer. I'll talk more about that later. And then they're fed in to the Qwen language model. So the language model will take in not just tokenized words, but also tokens that are generated or vectors that are generated from the encoded version of the audio here, which, as I said, is a Whisper model. Now, when they combine the Whisper model with the Qwen LM, they then do further training or fine-tuning. And so these weights are all adapted in the later stage of the training, where they will run through different forms of data sets that are listed here actually on the left-hand side. They'll use data sets such as combining input audio and a language prompt, like detecting the language and recognize the speech. They'll also include a data set around sounds, for example, animal sounds or the sound of a car horn. And then there are examples as well of supervised fine-tuning with chat formatted data, where there's going to be some kind of voice chat and then audio analysis asking maybe not just what's being said, but also what the mood is of the speaker. So in the end, this gives us a model where we can feed in parallel audio and text, or you can just feed in one. If you feed in text, it's like a normal language model. If you feed in audio, then it's a conversational model where you put audio at the input, but you get a response back that's in text. Now, importantly, versus Whisper, Whisper will just transcribe the audio. This will actually provide a response. So if I ask through audio, how are you today? The response in text will be, I'm doing well, or something of that nature. So let's take a look in a little more detail at how this model is set up. These are the pieces that correspond to the graph or the diagram I just showed you. There's the language model, which is pre-trained at Qwen 7b. There's the audio encoder. And actually, it's maybe a bit misleading for me to say custom, because it's actually a Whisper model that has then been fine-tuned once within the architecture. So the audio will come in, and that audio wave is jumped into windows, overlapping windows, and then the frequencies are calculated for each window, and the frequencies are converted to what the human ear hears. So they're rescaled for the human ear, which is called making a MEL spectrogram. And these MEL spectrograms for each of the windows are fed into the audio encoder. This is all standard for what is done in Whisper. And the result of what comes out here will be a set of vectors. And these vectors are then adapted using a simple linear layer, which just means simple matrix multiplication, to then convert them into a form that's compatible with the inputs of the LLM, which is Qwen 7b. So in other words, we need to transform the vectors representing the audio into the same space that the vectors coming out of the embedding layer for the text is going to be in. We want these to operate in the same space. Then we can feed these in parallel and predict the next token. Once that is predicted, we pass it back around the front and predict the next token again. And that's the autoregressive decoding. So it works exactly like a language model that I've talked about in many videos before, but it's now got these extra tokens coming in from the audio side of things. Now, How does that differ than just taking Whisper, getting some text and feeding that into a language model? For example, we could just run Whisper, take in some audio, calculate the transcription, take that transcribed text and then feed it into a language model. And that works well. I have a video on speech to speech where I even take it a step further and go from text output to audio at the other end. And you can do this, you can cobble models together, but one of the disadvantages is because you have these split models, it can be difficult to run them in production scale in a way that's going to parallelize the inference, which means handling multiple parallel requests. And that just means that if you're doing a hobby project, it's fine. You can get inputs in and inputs out. But if you want speed and you want to efficiently use your GPU, it's just going to be difficult if you have it split in different models. So here with the Qwen model, everything is encapsulated in one PyTorch model, let's say, and that model is then supported by a VLLM library, which we can then inference with efficient continuous batching. And I'll show that towards the end of the video. So yes, this is one of the two key advantages of the integrated model. The integrated model has VLLM support, so it's much cheaper to run if you want to do something in production. The other benefit is that because we can feed in both voice and text at once, we've a way to ask questions about the audio. So we can say what kind of bird was singing, or what was the emotion of the speaker, or we can just directly ask for the text to be, or the voice to be transcribed, but also to add in notes around how the speaker was feeling at that moment in time. Whereas if you look at just feeding in audio to a Whisper model, it only gives out text. There's no indication of what the emotions would be. There's no way also to feed in a question at the same time as feeding in audio, so you can't ask questions about the audio. So this gives rise to a few applications for this combined audio plus text model. The first is customer or assistant type applications, customer support, where the customer or you are providing voice input, and then there is text output coming back on the screen. And rather than going through two steps of first transcribing and then going to get a response, you go through one model. The second application is transcription with emotion detection. I'm going to show you an example of that in Colab. We can get a transcript and also get a description of the emotions. The third is sound analysis. I'm going to fine tune on some bird songs and see if we can recognize the birds. So you're able to do analysis like that, or acoustic analysis of machinery. You could ask, did that sound like something crashing or something breaking? Audio plus text assisted transcription. So we can feed in a transcript as well as, say, the text that's in a PowerPoint presentation. So if there's a speaker presenting like I am now, we can provide both pieces of information, and that's going to probably give a better transcript because it's giving a more complete context. And last of all, you can do things like zero-shot transcription. If there's a new word I'm using now that the model's unfamiliar with, I can just provide a list of new words in the text that would be in parallel to the audio I want to transcribe. So in that way, you can achieve zero-shot type behaviors. Just a note, we'll get to fine-tuning later. I will be using LoRA. So when we update the matrices, when we update the model for our specific application, I'm not going to update every single weight in all of the matrices. That would take too much computing power. Instead, what I'm going to do for every given key matrix, I'm going to freeze that matrix, not update it, and instead update these small adapters. These are called low rank adapters, and they have this rectangular shape here, such that when you multiply the two of them together, it will form a matrix that's the same size as the original matrix. And by just training these smaller matrices, we're able to get an update that is kind of a coarse update we will apply on top of the original matrix and merge them to get our final model. So we'll see that later in the fine-tuning part of the video. But next, let me just show you how this model can be run in a Google Colab notebook, which is free to run, and we'll run it in Colab in quantized format, before then getting into the meat of how you would build a data set and fine-tune this model for your application. And lastly, I'll cover in production inference of the model. So I've opened up a free Colab notebook that you can find in the description below the video, and this will allow you to run inference and see some different ways this model can be used. Now we're going to do some installations. First, we'll need transformers, we'll need bits and bytes. Actually, the model will not fit very well on the Colab notebook. We've got a T4 here with 15 gigabytes of VRAM. The model itself in 16 bits, it's roughly about that, so it's too tight. Therefore, we need to use a quantized version. So we need to actually convert each 16-bit weight into 4 bits so that we can fit it on the GPU. We're going to install HF transfer for fast download of weights, and we'll install accelerate, which controls the movement of weights between the devices being the GPU, the T4, and then the CPU, which is our computer. So I'm going to import here and import the operating system and set this environment variable. This allows for fast weight downloads and uploads. And next, I'm going to load the model. Now, just a few notes here. You can see the model is loaded using the Qwen 2 audio for conditional generation, and by passing in the model slug from Hugging Face repo. We're going to pass in a quantization configuration using bits and bytes. We're going to load in 4 bits. The compute type will be float 16 because we're on a Turing, that's a T4 Turing architecture. It doesn't support brain float 16, which is a more accurate data format. That's only supported by Ampere, Lovelace, Ada, or Hopper GPUs. Then we're going to use double quant. So there's actually quantization of the quantizations that happens within the model. And the data type we'll use is normal float 4. This is a normally distributed data type. So actually, when you quantize down to 4 bits, the 4 bits aren't just evenly spaced within the range of the value. So if you have some number, it's not going to be just, if you've got a range of 0 to 1,000, it's not going to split it into equal chunks. It's going to actually make those chunks normally distributed, which turns out is a better way to quantize. So we load the model like this. We load the processor. It's not a tokenizer, it's a processor because we need to not just tokenize text, but we also need to process the images into tensors. Sorry, not images, audio into tensors. And so we have a processor that will handle the audio, turn it into vectors, but it will also include the tokenizer, which is used for converting the text into tokens. So we load those up, and you can see here in total, what's that? 4 4s, 16. So it actually looks like even the model itself is over 16, 17 gigabytes in size. That's why we need to quantize to fit in 15 gigabytes of VRAM of the GPU. And that looks like it's loaded. I ran it before the video. So we can move on now to running a test on some audio. So I have some audio here, and if I play this audio, I don't know. So it's the voice of a Chinese lady who's speaking in English, and we're going to pass that in to the conversation. So we're passing in the audio URL here, and we're going to also pass in text asking to describe the speaker, including their age. So you can see that to do so, we have to load the audio data. So we've got the audio URL. We use the LibRosa library to load the data. You can also get the sampling rate just to check what that was. And I'm going to use this display function here. That's how I displayed this little widget to play the sound. So let's move ahead and actually inference that. And to run that inference, we're going to go through this script here. So we'll go through the messages in the conversation. That's these messages here. And we're going to make sure that when we hit the audio, so when we hit one of type audio, if it's a URL, then we're going to open the URL like this, and we're going to load it using LibRosa and append it then onto the audios. Whereas if we pass in audio, this is just passing in raw audio, then we'll directly append it because it's not a URL. Here's where the processor comes into play. So we have text. That's just straightforward. It's the text we input. And we have the audios, which we've already built up here. There's only one audio in this array of audios because I'm just passing in one file. And the processor is going to take in this text. It's going to take in the audios and it's going to convert them into tensors using the tokenizer for the text and then using the pre-programmed logic to convert the audio, basically take it through into frequency format, make the windows, convert it into the human ear MEL spectrograms, and then convert it into the vectors that need to go as inputs into the model. So this is all the preparation of the inputs that go into our model, and it's done by the processor. And these inputs can be passed into model.generate to generate a maximum. Actually, max length is the total of the inputs and outputs. So this is a maximum on inputs and outputs. If you want just max tokens, I think it would be max new tokens is maybe the argument. And then we will take these generated IDs, probably should say generated rather than generate IDs. And we're just going to focus on keeping the ones that are new. So remember, this is autoregressive. if you look at all of the generated IDs, then you're going to just get the inputs as well as the outputs, the new ones, and we just want the new ones. So we're gonna do that. Okay, so generated IDs, I need to make sure this is correct. And when I run this, I get a response here, and the response is, actually I need to run it again. So we're just getting a flag around passing the sampling rate. I'm not sure why this flag appears because I did pass the sampling rate in, and I don't see any issues with the generation, so I think it's fine. And here we have the response. The speaker is a female in her 20s, so that matches indeed with the sound that we saw, or that we heard. Now we can take an alternative route and actually upload a file. So here we're going to pass in raw audio. It's not going to be a URL. And what I've done for that is I've just, let me see here. I've uploaded a file called Tell Me a Fun Short Story. It's literally me saying in audio, tell me a fun short story. So let's run that cell. And let's see what it says.
Go ahead and tell me the fun shorts.
Go ahead and tell me a fun short story. And let's run that. So I'm literally asking for a fun short story, and that's what it should do. It should respond with a short story in text. This is an example of using a voice assistant that then generates text. So here's the story. Once upon a time, there was a little boy named Timmy who lived in a small village. So there you have it. This is the audio input and the text output. And there's one more example I want to show here, which I'm going to select by just setting this to true. So let's swap the conversation I'm selecting. And here I'm actually going to pass in the same audio of me asking for a short story, but I'm also going to pass in text saying, transcribe this audio and provide a description of the speaker's emotions and respond in the following format, transcription and then emotion. So let's try this one here. And it should run fairly fast because it's just a short little transcript. Okay, so transcription, go ahead and tell me a fun short story, and the emotion is amused. Okay, don't know if it was entirely amused, but at least it's following the format here of what we asked for around the emotion. And it's also doing fairly well instruction following for what is a relatively small model. It's a 7B model. So that's an overview of how you can run some different tasks. If you want to play around with what the model can do, you'll find this pretty handy. Note how if you look at the memory usage, we're only using about 6.7 gigabytes of VRAM, and that's because we've quantized, so we've cut in about 4 the size of the model compared to what it would have been otherwise. Next up, I'm going to talk about dataset preparation and fine-tuning. So this is how you can make a dataset that has audio and or text as an input and has some text as an output, and try to get the model to improve its performance for a dataset that you have yourself. And actually, the dataset I'm going to use is one I've pushed up to Hugging Face. It's called Trellis Songbirds. So it's a public dataset that I've put together, and I got it by going to Zeno Canto and looking for examples of birds that have songs available with licenses that can be used commercially. And what I did was push it so that I have the name of each bird. So here, like a red-backed shrike. And here I have a URL which links to the sound file. And my idea here is let's feed in the sound files for these birds. And we will feed in some text saying, what kind of bird is this? So we've got what kind of bird is this? We've got the audio. And then as the output, we'll have the name of the bird as the ground truth. So I have this data set. I've got 80 training rows, and I've got 9 validation rows. This script for making the data set is included in the advanced transcription repo. So if you go to trellis.com /advanced transcription, you can find details of everything available from this paid repo. You can get lifetime access to scripts that include dataset preparation for doing transcription, for doing voice cloning. That's if you want to read something out in your voice from text. There's also scripts around speech to speech, and now there are scripts covering this new task of audio plus text inputs. So you can take a look at this later on. And buying access to that will allow you to get into the advanced transcription repo, which we can check out here. And this repo now contains a folder called Audio LLM, where you can find scripts here for creating that birdsong dataset. And pretty simply, I'm just fetching a list of available songs for given bird names with the help of Claude. I'll very briefly show the script, but presumably you'll want to generate a data set for your own application. So you can see here, I've got a list of bird names. I definitely don't know any of these birds, but Claude suggested them. So I'm querying the API to get those at no more than 1 query per second, because that's the rate limit. And then I'm pulling down the information on the URLs and pulling down the information on the bird names. And then I'm putting that into a dataset format, a data frame format, which then I split into a training data frame and a validation data frame. And I actually save them to CSVs before later then putting them into a dataset dictionary format that I push up to Hugging Face Hub to a public repo. So we're going to train with inputs of text and audio. You could also train, and I'll show you this in the Jupyter Notebook, if you have some conversations where you have voice going to text, or if you have even voice going to voice, you can just transcribe the second voice and make that text and use that as your training set for this kind of application. So I'll show you how to make those modifications when we get into the fine-tuning script. Now, the fine-tuning script we'll work on is also in Audio LLM, and it's called Trellis Qwen Audio Fine-Tuning. I'm going to run that on RunPod, and I'm going to run it in this fine-tuning notebook. You can find access to this via the public repo Trellis Research one-click LLMs. So if you follow that link, you'll be brought to a page where you can select the GPU. It should be sufficient to have probably 20 or 24 gigabytes, but I'm going to go with this A40 here. It's an Ampere architecture that will have 48 gigabytes and easily fits the model. And this should be auto-selected, the fine-tuning notebook. So I'll just click deploy there on demand, and that should get me a pod up and running like I have here. So let's just connect to that pod via Jupyter Notebook, which should be ready in a second. And then I'll upload the script for Qwen fine-tuning that I showed you within the advanced transcription repo. All right, so I've uploaded the notebook that we need here, and we're going to run through the installation. And I want to talk in particular in this video about how the processor works, and how by looking at the processor, whose role is to take the audio and text and convert it into tensors or vectors, I want to look at that and explain how by looking at the processor, we're able to figure out how we should set up the data for training, specifically set up the data collator. So I'll get to that in a bit. First, you can optionally set up Trellis Assistant if you want a coding assistant in the notebook. We're then going to do the usual set of installs. We'll need transformers, the latest version, which supports Qwen Audio. We need Accelerate for device management, datasets for dataset management, parameter efficient fine-tuning, PEFT. We're not going to run with bits and bytes, but if you want to do quantization, I've put the option below. HF transfer for fast downloads, TensorBoard if you want to track the loss. Requests is for accessing if you want to get information from the internet using the Python request package. Matplotlib for plotting, and then Librosa, which allows us to load audio. I'm going to log in to Hugging Face. You don't actually have to log in unless you're going to push models up to Hub. I'm not going to push models to Hub, so I won't do it. But if you do, you just need to grab a token and paste it in. Next, we'll set this environment variable for fast downloads, and then we're going to load up the model. This is where you would load using the quantization config I showed earlier by passing it in. Now, I'm not using flash attention. I actually haven't fully tested it. It can sometimes give issues with Qwen, so I tend not to use it. And if you're ever reloading the model, if you want to clear out the GPU, you can run these lines. It can avoid you running out of memory sometimes when you need to reload. Just look at how fast these are downloading, 1 gigabyte per second. That's because you're using HF transfer. So next, we're going to run inference on the model, much like in Colab, but we're going to set up this function to do so we can reuse this function later when we want to run through a set of examples. And because I'm running on a set of bird songs, let's ask what type of birds you hear. And let's make sure that we pass in a bird song here, which is, I've just hard-coded a URL for now. Now, much like in the Colab notebook, we set up a conversation. It's got an audio and a text input, and we need to format, or rather process that conversation, make sure that any audio URLs there are, we're going to actually open that URL and load the audio with Librosa. And that will give us a set of audios, an array of audios. There's only going to be one in the array because we're just passing in one audio. and we'll pass that audio in here, and we'll pass the text in here to the processor, and that will allow us to generate the IDs or the numbers that are in the tensors that are required to be passed in, that will generate the inputs, which are then passed to the model.generate to generate the output IDs. And these output IDs then will allow us to get the outputs that we need in text format by decoding them using the processor. And this decoding is just using a tokenizer because the text is the only output. There's no audio output. So processor.batch decode is actually going to call the tokenizer to decode back into tokens. So let's see if we can run that example. And here we have the answer that's been given, and let's test. So I can hear a lot of just background forest noise, and I can hear maybe hear some birds. So these are all short snippets. Some of them are over 30 seconds. 30 seconds is the limit of audio input, so we'll have to actually trim the audio. You'll see that later. But yeah, just keep in mind, this is a hard challenge I'm giving the model because a lot of these are recordings in forests. They sometimes have crickets that are making noise. They sometimes have just got background noise. So it's really a difficult identification problem. Now here I just have some logging just to check the sampling rate of the processor. So this sampling rate rather for the Whisper model, it's 16 Hertz. So we're going to make sure that when we load any audio, I think the raw bird songs are maybe sometimes in 24,000 Hertz. So we're going to resample that down to 16,000 for when we input into the model. Okay, so that was an example of inference. Next, we're going to load the data set. We'll load a training split and a validation split. We'll then run the validation split and see how good the performance is with no fine tuning. Then we'll fine tune, and then we'll see if the performance improved. So let's load up these bird songs and let's inspect the 0th example of the train set, which is a Eurasian blackcap with audio available here. And now I'm just going to run in a loop running the example on each audio for each example in the data set. So let's go ahead and do that. I've defined the function and now we'll run the loop. So it's going to load each piece of audio. It's going to run the inference and it's going to also display the audio so we can play it. Let's just go back and take a quick look. I want to show you where we have the resampling. I've explicitly done it here. So I've got the audio is being loaded like this. And then when it's loaded using Librosa, I'm then resampling to a target sampling rate, SR, where SR is set by whatever the processor expects. So processor.featureExtractor.sampling rate, that's a feature of the processor, which we've loaded up above. Remember, when we loaded the model, we load not just the model, but we load the processor. And it's got defined what sampling rate it expects. So here we're resampling. Now this is an explicit way of resampling. Actually, when you load, you can just pass in the sampling rate as well. And I think that's done by passing in here. You would do SR is equal to SR, and that would do it for you. So that's another way you could just resample when you load, but I'm loading and then resampling in this case. Later, I'll just do it in one step. Okay, by now we've run all of the evaluation examples. And as I said, generally it's getting them pretty much wrong. We'll see if fine tuning improves that. So let's inspect the processor to help us understand how we should prepare the data, specifically how we should prepare the data collator that passes the data into the trainer. And something I like to do is to start by inspecting the tokenizer's beginning and end of sequence tokens, as well as the pad token. So I've just printed those out here and we can see the numbers. There is no beginning of sequence token. And that's actually because this follows a kind of chat ML type format. You can see all of the tokens by going to processor.tokenizer and printing that out. And while there is an EOS token and there's a pad token that's actually using end of text, we're using these special tokens to do the templating. So there's the chat ML, IM start, IM end, and there's actually a specific token then for audio, and there's one for audio start or audio BOS, beginning of sequence, and audio end of sequence EOS. So there are very many tokens here. These are probably used for doing some audio timestamping, but I haven't dug too deeply into that. We'll see these tokens reappear when we look at chat templating in our data collator. So the first thing to do if you're trying to train a model and you're wondering, how do I build a data collator? You have to look at the processor. because the processor is what is going to prepare the data. And this processor needs to prepare not just text, but also audio. What I like to do is load up a test sample. So here I'm just loading, first I'm opening the URL, and then I'm loading with Librosa the audio. I'm making an array with just this audio within it. And the array is going to be called audios, and I'll pass it into the processor along with some text that is just this little test piece of text here. And when I print that, I can see what the processor outputs. And the processor outputs a few things. So input IDs, you'll be familiar from language models. These are literally the tensors representing the inputs in text. There's the attention mask, which makes sure that when we're predicting, it makes sure that when we predict the next token, we're not automatically or accidentally feeding in the actual future tokens, which would allow the model to cheat. So the mask makes sure you can only look backwards. Then we have input features. These are actually audio features, tensors representing the audio. And the input features also have an attention mask, only allowing look backwards, called feature attention mask. So when we prepare our data, we need to prepare the data collator to generate these things, the input IDs, the features and the masks. But we also need to prepare labels. Labels are the outputs, the ground truth outputs that the model is going to be compared to with its predictions. And that's how we will calculate the cross-entropy loss and then penalize the model and backpropagate to update the weights. So that's what we're going to do in this audio data collator. And the purpose of the data collator is eventually to be passed into the trainer. So if we go down to the trainer, you'll see here, right towards the end, we'll pass in the data collator. And the data collator will be initiated right here. Data collator equals audio data collator, which is the data collator class we're defining. And it's going to take in the processor and it's going to take in a task prompt. And I'm making it take in a task prompt because the task prompt will be the same on every question. It's going to be identify the bird species in this audio clip. So let's look at how we actually prepare the data in the data collator. And I'll step through it fairly slowly. It's a lot of detail, but I think this will be useful because in principle, it will let you prepare any data collator for any model. So we'll initiate a class that has a processor, which is the processor from the model, the task prompt, which I described, which bird type is this. There's going to be a max length, which will just be the processor max length, or we can override with our own max length here. It's probably a bit of an extra feature we don't need. And then there'll be the sampling rate we'll define for the data collator, which will be set by the processor's sampling rate here, feature extractor sampling rate. Now the processor feature extractor, which is the audio extractor, it also will have a maximum length, which is n samples. This is the length of the transformed audio. It corresponds to 30 seconds worth of audio. And we're going to make sure to clip the audio if it goes beyond this length. We'll see that later. So we've got this class that will be initiated with these properties, and it will also have this function called process audio, which simply takes in a URL, loads up the audio, and if the audio is too long, it's going to truncate it down to the max length, which is the max length of the processor. There's also a call within the definition of the audio data collator, and the goal of this call here is to take in the data rows and output way down here the input IDs, the feature, the input features, the masks, and then the labels, what we already said earlier. So the question is, how do we prepare all of these? And the answer is, we prepare the input IDs, the masks, and the input features just using the processor. I'll show you that. And then we prepare the labels here actually by copying the input IDs, and I'll explain that in a moment. So let's first look at how we prepare the input IDs and input features. To do that, we're going to start reading in the examples one by one, reading in the audio and putting the audio into an array. So we've got this audios list. There's only one audio per row, by the way, so it's an array of one. Then we need to set up the conversation. So this is preparing the text. And the conversation will contain the example audio, and it will contain the task prompt. So we've got a text input and we've got the audio, which is the bird song. And the conversation will include the answer, which is going to be example name. So if we look at the data set, there's a name column here. That's the ground truth bird's name. We've got a URL column, which is the URL. With the conversation in hand, we need to chat template it. This is what converts, it rather adds in any special tokens that we saw above, and we'll see an example of that printed later. But basically we take the conversation and we apply the chat template that's defined in the processor. By the way, if you ever want to print out the chat template, you can do something like this: print processor.tokenizer.chat template. And you can see here that this is the Jinja template that's going to be applied. And it's allowing for system messages. It's always wrapping every turn in IM start and IM end. And if we have a generation prompt, it's going to add in IM start and assistant. So that's the chat template. Now, once we have the conversation templated, but not tokenized, we've got tokenize equals false because we'll tokenize in the processor. We're going to just append that on. So we have our combined text, which will contain the rows of data of combined. Why is it called combined text? Because I'm combining not just the question, but also the answer. That's why I've called it combined text. Now, if you turn the debug variable to true, you can also see some printing. You can check that the length of the combined text matches the length of the audios, which it should in this case. And now that we have combined text and we have audios available, these are still not converted to tensors. We want to convert them to tensors. And the way we do that is by using the processor. The processor does the heavy lifting. It takes in the list of combined text, the audios. It's a list because we're processing all of the rows at once. And it's going to return tensors in PyTorch format, and it's going to pad them if necessary to the same length. Now, when I say it does the heavy lifting, that's because when it generates the inputs, so it's generating inputs, those inputs already have features. They have the features that we need. So the inputs will already have the input IDs, the input features, and the masks for those. What it does not have is the labels. So we need to set up the labels. So all of this here is just debugging. I talked about that. We calculate the inputs here, which are the tensors. Now we need to prepare the labels. Now, the way the labels work in a regressive process, that is decoder only. Decoder only means we pass in inputs, we get one output, we pass it back to the front, we get another one, we pass it back again. And the nice thing about autoregressive processes is that if you have some complete text with the answer, that's basically what you're going to use as the labels. So the inputs and the outputs are going to be the same, but shifted by one. And actually the shifting is typically handled automatically. So normally all we need to do is copy the inputs we have, including the answers, and we need to make a copy of that to become the ground truth. So that's exactly what we do here. We do labels equals inputs, and then we clone them to have a copy. And again, we can print out if we want to debug. But there's one more thing we need to do, which is when we clone the inputs to make the outputs, that's going to contain all of the question and the answer. But actually, we only want to penalize the model on the answer. So we need to do what's called masking. And actually, rather than create a mask for the labels, what we do is any position, any of the early positions where the question is, rather than create a separate tensor with a mask, we just set all those values to -100. -100 is the ignore index. And if you set anything to -100 in the labels, the trainer will know to just ignore that. So here's how we make the labels. We take the inputs, which has question and answer, we copy it, and then all of the question portion, we're going to just get rid of it, or not get rid of it, but putting -100 for each of those tokens. And that's essentially what all of this code here is doing. It's a little bit more nuanced because the way we check where to put all the -100s is we have to check in the chat formatted text, and we have to look for the start of the assistant response, which is going to be given by IMStart assistant. And we're going to search for this. And once we find this, we're going to put -100 for this and everything before it. That's what all this code here is doing. It's putting in -100s for everything up to and including IMStart and assistant, so that only the labels afterwards are going to be used for calculating the loss. And you can see here, like I've got an error. If it doesn't find this, well, something went wrong with the chat templating, so we should throw an error. Okay, so with that, we can pass the labels in addition, and we've got everything we need that the data collator should produce. And once the trainer sees this, it's going to recognize there's labels. Let's use that for the cross-entropy loss, and let's use all of this here for the inputs. Now I've defined a batch inspection function here that just prints out some data, and let's talk through that together. it will simply show all of what I've described. So here I just run the data collator on one sample batch size of 1, and you can see here are the input IDs. So I've got this task and I've just put in one audio sample. So the first row here of the input IDs, you can see it's a tensor. Notice there are some special tokens here. Like I think this is maybe a beginning of sequence token. I think this might be a beginning of audio and end of audio token. This might be an end of sequence token. So yeah, you'll see some special tokens in here. The attention mask, it's just showing the first row. So we're always paying attention to all of those previous tokens. The input features representing the audio, the mask, which masks the audio, and then the labels. And notice how the labels here, they're all 100, minus 100, because we're ignoring all the inputs. And then we do have labels for the final tokens, which correspond to the answer. And the answer is quite short. It's actually just Great Black Hawk. So basically, these tokens here, these should all correspond to Great Black Hawk and also this IMEnd token here. Whereas all of these tokens here in the inputs, these are all going to be set to minus 100 because we want to ignore them for the loss. And you can see when I decode the labels and ignore any of the minus 100s, it's correctly just showing the output that I want the loss to be computed on. So that's the setup of the data collator, and we're ready to push that into the trainer. So the trainer is going to take in the model, it's going to take in the data collator, the training data set, and the evaluation data set. And it's going to run the training, and it'll also take in the training arguments, which describe some of the hyperparameters I'll discuss in a moment. But first, note that we're not going to train the full model. We're going to freeze the model first and apply adapters, which is called applying LoRA. And we're going to do that here. First, we can print the model just to take a look. Notice how it's got an audio tower. So this is the audio model, and it contains attention and also feed forward, fully connected layers here. And then there's this projector. So this links the audio model to the text model, and it's actually a simple linear layer. This is a bit less common because it's known that using a multi-layer perceptron is typically better, but I suppose just a simple linear layer is enough. We will actually make adapters on top of this to train it. And then there's the language model, which has got attention here, and it's got multi-layer perceptrons right here. So we're going to train all the linear layers. So anything that's marked linear, we're going to want to add adapters and make those trainable. And that's exactly what we're doing here. We're going to target all the modules that have linear layers in them and create these low rank adapters, those little rectangles. And the rank, which you could think of the height or the narrower dimension of the rectangle, is going to be 32. That should be plenty. We'll use rescale LoRA. We'll set LoRA alpha to 32. You can check out my video on, I think there's a recording on LoRA. It's a live stream if you want to understand those parameters a bit more. And we'll use a dropout, which should improve. It basically drops out some of the weights to avoid overfitting. And the task is causal LM. We're not going to use bias. It's not supported. Is it supported? Yeah, no, it is supported because we're not using unsloth. So we could add in a bias in the adapter layers, which means they're not just linear, they're actually affine layers, which may or may not improve performance a bit. So once we've defined this LoRA configuration, which is another way of saying we've defined these rectangular adapters we want to train, we're going to apply it to the model. This will do a few things. It will freeze the main matrices, and then it will apply these adapters and make them trainable. So we can run that. It'll take a few seconds, and we can run model print trainable parameters to see how many parameters are going to be trainable out of the total parameters. The total parameters now will be a bit larger because we have added these adapter parameters, but only the adapter ones are trainable. So that's why we've got about 1.3% are trainable. So now when we pass the model in, it's going to only train those adapters. And we're going to do some training here first for one epoch with a constant learning rate schedule. So a constant learning rate of 2e minus 5, which I like for 7 billion parameter models. We'll do a batch size of 4, which gives some smoothing, some averaging. I've created a run name here. And what else should I say? Here's the name of the model for the hub if we pushed using the trainer. Yeah, we're going to set gradient checkpointing to true. This is going to save VRAM. It means that we throw away some of the calculations on the forward pass and recompute them on the way back. That reduces the amount of data we need to store in the GPU. But we're going to turn off using reentrancy. Is an optimized way of recomputing the activations on the backward pass, which we have to do because we're using checkpointing and we've thrown them out. And yeah, normally it speeds things up, so we like to use it, but it is more complicated and it gives issues with the Qwen model. So we have to set that to false, which will slow things down a little bit. So then we're ready with the trainer. We pass in these arguments right here, and we can run trainer.train. And I can just run that now. I'm running on an A40, so it's possible I might run out of VRAM because I ran this yesterday with 80 gigabytes. But let's see what happens. We can take a look at the GPU and looks fine for now. Actually, I possibly could have given a larger batch size. Let's wait until we get through the eval, see if it was too much of a batch size. Still looks fine. I'm running the eval every 0.2, I think, or 0.25 of steps, 0.2. So every 20% of the run, there should be an evaluation. Yeah, and there it is. So looks like that is training fine. So what I do is I run through that training, and when the training is done, I actually rerun the training, but I rerun it now for another epoch with a cosine schedule. So I'm training like this, constant learning rate, and then dipping down with a cosine. And this lowering of the learning rate is called annealing. It basically brings the model to a more delicate optimum that often improves the performance of training. So once that's done, you can run evaluation again, and we can see the performance and whether that has improved with the benefit of doing this fine-tuning. Now, while that's still running, just a few quick notes. You do want to set the model to evaluation mode, which means there will be no gradient storing or updating before you run the model evaluation loop again. And once your training is done, I've given an opportunity to log into Hugging Face again if you haven't. You can use trainer.push to hub, but this will just push the adapters. Anytime you've got adapters that are not merged, it will default to pushing the adapters. So if you want to push a merged model, you should run model push to hub. Model.merge and unload, and then model push to hub. And don't forget to push as well your processor along with the model so that people are then able to download and inference the model from hub. So we're just about to finish training here. And what I'm going to do, as I said, is I'm going to run this annealing step. So let's comment in the cosine learning rate. Let's run that cell, and then let's restart the training. And then we will run the evaluation. And I'm going to come back and take a look at those results. But in the meantime, let's go and take a look at how we can inference these models using VLLM. So whether you want to run your fine-tuned model or whether you want to run the base model, which you can do very quickly, you can do so by going to the one-click LLMs repo. This is the public repo, Trellis Research, and search for Qwen to audio, and you should be able to find this template here. And if you Command or Control click on that, it's going to open up a window where you'll be able to select the GPU, and an A40 is fine for this. You could probably even go smaller with a 20 gigabyte or 24 gigabyte GPU, and it will open up this template here. So I'm going to get that running. I've actually got it running already, and we can take a look at what the template looks like here. So we're going to serve the Qwen to Audio 7B model. We've got this served model name parameter here, which just sets the model name that you query when you're hitting an OpenAI style endpoint. We'll see that in a moment. We're going to run the API service on port 8000. You actually, I don't think, have to pass trust remote code, but this ensures we can run remote code if that's necessary. We're going to run with enforce eager, which means we're not going to use CUDA graphs, which will make it start up faster, but could reduce the inference time a little bit or cost VRAM as well. And there's also this parameter to limit the maximum number of audio inputs, which relates to the VRAM that needs to be reserved. So you'll need to reserve more VRAM if you put this to a bigger number. So I've just set it to 5. We're only going to be putting in one piece of audio at a time. Now the disk needs to be at least 20 gigabytes because it needs to fit about 16 gigabytes of weights to be downloaded. And you need to use a Docker image. Now normally here you would use the VLLM Docker image, which you can get from VLLM/VLLM-OpenAI. But we need LibRosa to be installed, and LibRosa is not installed on the base VLLM Docker image. So I've created a Docker image. It's this one here that includes LibRosa within it. So with that done, you can start up the container, which I have already done. It will download the weights. You can see they just about fit. And then you will see that the GPU starts up. And I've actually been running a bit on this already, so you can see some different prompts. And let's see where the GPU started up initially. You should see this line here, UVcorn running on port 8000, and that means you're ready to go. Just one other small note, you do need to expose the port 8000 here. And all of this is done if you're just clicking on the one-click template. Everything is going to be pre-configured. If you want to run your own custom model, you should swap out the names of these models right here. Now, if you go again to that template, which I have open here, you can see there's a README file, and the README will have some guidance around how you can run inference. So here I've got a curl command that I can use to hit the endpoint with a sound file here that's of glass breaking, and then some text asking what is in this audio. And there's also some Python code you can use if you prefer that there. So I'm just going to copy this curl command here, and I'm going to paste it into a text file. So let's just quickly make a test.py or .txt even. And if I can open that file now, I'll just paste in the curl command. And you'll see the reason I'm doing that is because I need to grab the pod ID. So over here, I'll go to my pods, and I'm going to copy the pod ID and paste that in as the pod ID placeholder here. And now I can take this curl command and head over to a terminal, and I can just start a new terminal and run that command by pasting it in. And let's see what kind of response we get. So here the assistant says the audio contains the sound of glass shattering. So everything is working well here, and that's how you set up inference. And as I said at the start of the video, the big benefit to having this integrated model is you can run really fast inference with parallel dynamically batched requests. So you can get very good GPU utilization compared to cobbling something together where you have, say, 2 or 3 different models. It's very difficult to run that in an efficient batching way on a GPU, whereas this will run really efficiently and cost effectively with VLLM. So with that quick demo done, we can go back to the results of our fine tuning. You can see here, I've now been annealing for the last epoch. And to be honest, it's not entirely convincing because my training loss is going up, which is a bad thing. And possibly my validation loss is a bit unstable. So unclear whether that really is helping here, the annealing stage, but we can always check the data for ourselves. And here we go. So it's predicting a bullheaded shrike, and the answer is a red backed shrike. So not too bad. Yeah, I mean, there's background noise, but I definitely wouldn't recognize it. This one here, a bird that sounds like a cricket, that's clearly wrong. Bullheaded shrike, wood-head warbler. It's thinking a lot of these are bullheaded shrikes. Cricket, black redstart, Blythe pipit, Eurasian blackcap. So you can see if I've correctly run that again, the results on this maybe are a little bit improved. It's getting one of them correct versus what we might hope for. All in all, the data that I've used is probably insufficient. I've got maybe about 80 rows, but at most I've got 10 for a given bird. And some of the birds, there are only 5 audio samples that are being represented. Another problem is that some of the audio snippets are very long. They're a few minutes long, and we're only able to capture 30 seconds. And I haven't checked whether the 30 seconds we're capturing is the 30 seconds that has a lot of the bird song or just a lot of background noise. So I did run this earlier. I think I may have run for a different number of epochs, maybe got a bit better results. But all in all, this is an example of needing a bit more data to get higher performance. Now, there's something I want to say. If you're going to fine tune for some other applications, you're going to need to tweak the data collator. So let's take a quick look at the data collator for how you can do that. You'll notice we defined the same task prompt in every case. But if you're going to have a conversation, then you may want to have no task prompt. You may just want to have audio. And if you have just audio going in, you can simply remove the text portion here that you have to provide. This means you would have a data set that's going to provide maybe a URL to the audio, and it would provide some target like the output, like a name, or it could be the response of the assistant if you're doing voice in and assistant's response out, and you would not need to provide any text input. So you could simply comment that out, and instead of using maybe a name as an output, you could choose to use some conversation output as the output that you want to train on right there. Now, just a final thing, I'm going to download a copy of this notebook without the outputs. It's actually a large file because it's got all of the audio built into it. So I'm going to download a version of this to repo for those with access that's just got outputs in the name. That will allow you to upload it more quickly if you don't want to wait on the embedded audio files to be uploaded as well. And that's the end of this video on how to fine-tune and deploy audio plus text input models like Qwen. I've gone to quite some detail describing how you can set up the data collator, and I hope that can be useful as you do other multimodal model training as well. Now, this model I think is underappreciated because it is a clean single model that takes in audio and allows for text output and runs very efficiently using VLLM. So you can check out the one-click LLMs template available in the public repo if you want to try that for yourself. I've put a link to the Colab notebook below so you can play around with different functions. And then, of course, if you want access to the detailed scripts, you can head to trellis.com/advanced transcription. In the meantime, let me know of any questions below down in the comments. Cheers.